So we need a way to count atoms, and I'm going to have to wrestle with this for a while because there's a number of things embedded in this whole idea of what an atom represents and how do we efficiently communicate all of those things. Look at a periodic table, back of your book, if you have a book, or out there on the internet, and if you get a good one, you'll see that one of the most important numbers is the number typically right above the element symbol in the center, or perhaps over on one side, the atomic number, which is an integer. The periodic table is arranged in order of increasing atomic number as you go left to right, top to bottom. And that represents the number of protons, which, as you recall, have a mass number of 1 and a unit positive charge. And that atomic number then, oftentimes referred to as Z, has a one-to-one correspondence with the element. That is to say, the atomic number uniquely identifies the element. The atomic number is known, the element can be deduced, and vice versa just by looking at that periodic table. The elements take their identity from the number of protons, and one interesting fact of nature is that there can be varying numbers of neutrons in the nucleus mixed in with those protons. Each of these then represents a different isotope. It's probably a word you've heard before. And although most of the time, almost all of the time, the isotopes are not chemically different, it's worth noting that there are differing numbers of neutrons, and this is what makes the idea of the mass of an individual atom or a group of atoms a little bit tricky. The mass number, then, is simply the sum of the protons and neutrons in a particular atom and would always be an integer by definition. We call those protons and neutrons nucleons because they live in that nucleus. If we pursue this further, we'll see that the most efficient way to communicate information about a particular atom or a group of atoms is through isotope notation. And here we simply take the element symbol, shown here the example is zinc, and then put information around it as needed to communicate whatever we're trying to communicate. Sometimes it's a very simple thing, in which case we don't have a lot of information around it, and other times there is more than meets the eye here. In any event, if you look at your periodic table, you'll see that the atomic number for zinc is 30. And if it is included in the isotope notation, we put it in the lower left-hand corner there, although I remind you that we don't ever have to include it if we know the element symbol, because zinc is always 30, and atomic number of 30 corresponds to zinc. So this information is often omitted because it is somewhat redundant if we know the element symbol. Up in the upper right-hand corner, upper left-hand corner is the mass number, which again is the number of protons and neutrons. Note that we don't write the number of neutrons anywhere in this isotope notation because we can easily figure it out by simply taking the mass number, which is both protons and neutrons, and subtracting the atomic number, which is just protons. So for example, this isotope of zinc would have 36 neutrons, 66 minus 30, and 30 protons, giving us a mass number of 66, and we could in fact refer to this as simply zinc 66, telling us exactly the number of neutrons by subtraction. In the upper right-hand corner is the place where we will put charges should an atom have a charge. If nothing is shown, we assume that the atom is neutral. And remembering about the charges of our atomic particles, if this atom of zinc is neutral, it has to have exactly the same number of protons as electrons. And so it's implied in this symbol, if nothing is written there, that this atom of zinc has 30 electrons. 30 electrons of -1 charge plus 30 protons of +1 charge gives us overall charge neutrality, and hence this atom doesn't have a charge. We're going to discover that atoms readily get charges, become ions, as they gain and lose electrons through a variety of mechanisms. And if that were to happen, we would record the charge of the ion in the upper right-hand corner. For a variety of reasons, metals commonly lose electrons, and hence, if this zinc atom were to be so unfortunate as to lose an electron, we would write here +1 to indicate that it now has one fewer negative charges than positive charges, and hence its charge is +1. Another way of putting that, this zinc atom has 29 electrons, and because there's one more proton than electron, or 30 of them, it has a charge of +1. We'll keep track of those charges and talk more about how atoms gain and lose electrons in various chemical changes, but for now that gives us all the information that we need to keep track of. A little practice then for us to get comfortable with this idea. We're going to need a periodic table, which I neglected to round up before I started talking. Let me quickly grab one. I'm back. Here's my periodic table here. Fluorine, you go to our element symbol there, has this chemical symbol F, right? And its atomic number is 9, so that would go there. And notice if we take the 10 neutrons and add the 9 protons, we would end up with 19, and so this symbol would then give us the isotope notation for a fluorine atom with 10 neutrons. Notice, of course, then the subtraction giving us those neutrons based on them all having a mass number of 1, the same and no charge. Copper with 64 nucleons equal to protons plus neutrons, and so I go to my periodic table, find copper, has atomic number of 29, and so I write Cu, 29, and then just put the nucleons up there in isotope notation. Remember, those protons and neutrons each have a unit mass. Silver with 60 neutrons and 46 electrons. Again, I go to the periodic table, which you of course can't see because it's getting the projector thrown on it. Find silver, I got Ag, has atomic number of 47. There are 60 neutrons, so the 60 plus the 47 gives us 107, right? And only 46 electrons, so this silver atom has lost an electron. And I would write up here in the right-hand corner, 1 plus or +1. There's a subtle difference between those two, but I'll let you do either one. And now we have a complete picture of the status of that isotope of silver. We could do this all day long. Now here's an exercise going backwards from the isotope notation to the protons, neutrons, and electrons. Remember that the number of protons is equal to the atomic number, so that's easy. The number of neutrons has to be solved for by subtraction. Here in this case, what? That's 45. It's worth noting that almost always the number of protons and neutrons is not the same. Maybe more information on that much later in the course. And notice that in this case, because the charge is 1 minus, there's got to be an extra electron. So there must be 36 electrons and 35 protons, which gives us then this charge. And we'll discover that those nonmetals over there in the upper right-hand side of the periodic table very often do gain electrons to become ions. Another example very quickly, Cr3+, again, pretty easy, 24 protons. That atomic number then, again, largely redundant because we have the element symbol. Number of neutrons then would be the 52 minus the 24, going to give us what? 28, right? And finally, the number of electrons. Notice this chromium atom has been so irresponsible as to lose 3 electrons. It has 3 fewer electrons than protons, hence the positive 3 charge, and it must have then 21 electrons in order for this element symbol to capture that. So you can see, once we master this, we have a very, very, very efficient way of conveying a lot of information in a really, really small space. And I reiterate that charge information is going to be very, very important as we think about how compounds form. I'm going to stop right